Welcome to today's webinar, GPS Anti-Jam and the Latest in Sensor Fusion Testing, brought to you by GPS World Magazine and our sponsor of the event, Spirent Federal Systems. Spirent Federal Systems specializes in GPS and GNSS test technology and serves the needs of their customers with market-leading GPS and GNSS test solutions. Their GPS test systems support encrypted military codes, interference simulation, GPS applications, and high dynamic testing. I'm Mackenzie Schoner from North Coast Media, content marketing producer for GPS World, and I will be the moderator for today's event. Before we get started, I wanted to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. At this time, I'd like to acquaint you with the ways in which you can participate during today's presentation. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during the presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and assistant producer Allison Barwatz or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of your console. If you are logged into your social media accounts, you can share this webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see in the bottom right-hand corner of the screen. Now I'd like to introduce you to today's presenters. We will be hearing from Chad Pillsbury, Senior Director of Resilient Navigation and Reconnaissance Solutions for Raytheon Intelligence and Space. Chad helps provide customizable open architecture navigating, timing, radar, early warning, and EO/IR solutions for military airborne weapons and ground-based programs. Prior to joining Raytheon, Chad served in the U.S. Air Force. We will also be hearing from Ben Graham, Director for Advanced Navigation and Surveillance Systems for Raytheon Intelligence and Space. Ben is responsible for M-code development programs on the ground, weapons, and avionic, as well as the AS/ARS radar programs. Ben also serves as the Deputy Subproduct Line Director for Resilient Navigation and Reconnaissance Systems within the Secure Sensor Solutions product line of Raytheon Intelligence and Space Programs. Also from Roger Hart, Director of Engineering for Spirent Federal Systems. Roger joined Spirent Federal in 2015 and has responsibilities in engineering, development, and support, sales, and customer training. We will also be hearing from Ajay Vemuru, Director of PNT Simulations for Spirent Communications. Ajay is the Director of PNT Simulation at Spirent Communications, who helps the robotic community build safer and more reliable location-aware platforms. At this time, I'll turn the presentation over to Chad Pillsbury, Senior Director of Resilient Navigation and Reconnaissance Solutions for Raytheon Intelligence and Space. Chad, take it away.
Thank you very much, Michelle. It's an honor to be part of this, such a large group of people who are passionate about navigation. I am Chad Pillsbury with Raytheon Intelligence and Space. I'm going to quickly discuss the first couple topics here on our agenda, the Raytheon Technologies organization and our merger, which were special interest topics, and we'll build on what some of you heard if you were on the last webinar late last year on that topic. We'll give you the second half of the story, and then I will turn it over to Ben Graham, who's going to discuss the technical aspects of this, our capabilities, the roadmaps, threats and mitigation, and fusion, as was mentioned earlier, as a special interest topic. Raytheon Technologies is now newly formed Raytheon Technologies, a large aerospace and defense company on the order of $100 billion of sales that combine the former United Technologies and Raytheon Technologies. And we do provide all types of advanced systems and sensors and services for all of these different types of customers, government and commercial and military, worldwide. Raytheon Technologies, as you have heard in the last webinar, is made up of 4 businesses: Collins Aerospace and Pratt & Whitney from the legacy United Technologies, and Raytheon Intelligence and Space, and Raytheon Missiles and Defense from the former legacy Raytheon Corporation. Our business, we are part of Raytheon Intelligence and Space, which was combined from 2 former businesses. For those of you who have been customers of ours or partners of ours, this is the former Space and Airborne Systems and Intelligence and Information Systems businesses combined into RINS. Raytheon Missiles and Defense, for your information, comprises the former Raytheon Missile Systems and Integrated Defense Systems businesses. And from an organizational standpoint, in our military navigation department and business area that I run, we have not changed in our direct reporting. We still report to the same Vice President Eric Dittmars in Secure Sensor Solutions, and the President of Raytheon Intelligence and Space, Roy Azevedo, is still our boss. He was our leader as part of Space and Airborne Systems before the merger. Raytheon Intelligence and Space, we like to say any domain, any challenge, and we take on the customers, tackle the customer's toughest problems. We do deliver advanced sensors, training, cyber, and software solutions to a wide variety of customers. We are roughly a $16 billion business at RINS and about 39,000 employees. We're headquartered in Arlington, Virginia, and we have major centers of excellence and centers of engineering and manufacturing in Texas and California, Colorado, and Mississippi. So now I'm going to turn it over to Ben Graham, who is going to talk a little bit more about the cooperation and collaboration that we have in our new organization with our teammates in Collins Aerospace and where the technology is going. Ben?
Thank you, Chad. Thank you, everybody, for taking time this morning or this early afternoon to listen to Raytheon and the technologies and the capabilities we're trying to align. Encourage folks to follow up afterwards if there's any questions. We would love to talk to the customer community and understand more. Very excited to be here today. Very excited to be in the job that I'm in. As Chad said, I'm in charge of a lot of our future new business vision programs, as well as some of our key execution programs. Even more exciting is welcoming and joining Collins to our overall platforms. Historically, on this chart, on the left side of the chart in the red, is the Raytheon Space and Airborne Systems legacy capability. Starting with ASICs, systems on a chip, FPGAs, and MEMS, we focus on secure capability at the lowest level of the component. Where power really comes in, cost and the system architecture is at the receiver level, where we have a number of products ranging from Y code to M code. And what drives the overall requirements is really the platform and the unit level, where SWaP-C, size, weight, power, cost, and mission performance drives a lot of the capability. Where alternative navigation, assured navigation, and resilient navigation is really going is to address a systems of systems concept. And we're going to talk a little bit about that today, which in the last few years has really changed the requirement set for what we traditionally do in a GPS-based navigation area. Having this full vertical integration gives us great capability to work with our customers to bring kind of advanced capabilities, some unique ConOps, and really to participate in the future of the battlefield. We welcome Collins and are glad to join them at our sides with the blue targets. their mission systems is a great superpower, and the ability to plan for, design for, and produce units, platforms, and they join us at the System of Systems ConOps. In the last webinar, you saw some of their capabilities which complement ours, and we're going to talk a little bit about that today. But we're really excited in 2021 to bring these two great companies together to try to offer you as customers, you as an industry, capability at cost. And really, we do that through anti-jam, sensor fusion, anti-spoof, and some of the advanced signals that are coming out in space, land, air, and ground today. As I move to the next chart, I'll pull on that thread a little bit. In the upper left, you'll find the legacy Raytheon Technologies that we're very proud to have. The top two really focus on anti-jam. We like to consider ourselves a premier anti-jam house. We have some unique algorithms. We have some unique capability that really allow us to outperform a lot of the threats that are in the battlefield today. We also focus, as I said before, on receivers. We do work with CA, commercial code, legacy Y, military code, and the future M code capability. We also work with commercial signals, GNSS, L1C, L2C, as well as future satellite constellations that are in planning now or currently in orbit. With all those signals and that anti-jam technology, PNT fusion becomes the key enabler for the next decade. And to do that fusion, we need to make sure that we have the right antennas, the right systems, and riding at the forefront of that capability is time transfer. And we'll talk a little bit about what that means. Finally, alternative navigation is becoming a larger and more important thing in our industry today, whether that be true alternative navigation or signals of opportunity or sensors of opportunity. All of those need to account for what we have. Collins is unique and has a very tried and true history, especially in their MAPS and DAPS programs. If you're not familiar, the mounted and dismounted assured PNT systems, their legacy JPALs, some of their underwater programs, and really their outstanding product in Link 16 and their tactical targeting network. Bringing those together, the new company moving into 2021 will have great technology enablers in the form of time transfer, safety of flight, avionics certifications, and we're really focusing on what it means to have fusion, alternative navigation techniques, and GPS-denied capability to augment what we call the golden standard of GPS. At the forefront, anti-jam is key. If we can block enough of the bad signals, we are able to achieve the golden standard. If it's not available, we'll move to the alternative navigation, and that's what we're going to talk a little bit about today. And in the end, we are very cognizant of cost, development and productization, and producibility, because if we can't make it, it's not going to be a benefit. So that remains at the forefront of the enablers that we like to hold strategic. So together, Collins and Raytheon are really trying to see the future and drive the future so that we can have products ready. What do we see that future as? Moving to the next chart, I really appreciate the feedback we get from our customer community, both the U.S. government, foreign governments, primes, and users of our products. Across this chart here, you'll see three graphics. There are many, many more. But at the presidential executive level, at the congressional level, there have been a number of mandates that have come out in the last 2 years asking for the United States to look at alternative capabilities to GPS if the worst were to happen. There's an action to call back on what industry can do to meet that call to arms and what technologies we could bring to bear quickly and cost effectively. In the middle chart, you heard Colonel Collins speak at the last webinar. He went through the GPS Enterprise Roadmap. Some of the key capabilities coming off that roadmap, some of the key drivers and capabilities of the future are GPS Block 3F. The U.S. Air Force is really looking to bring to the forefront advanced capabilities at that cut-in point to round out the M-code constellation of the future. Some of those capabilities include commercial signals, Some of them include specific M-code requirements, and some include futuristic software type applications. In the end game, there really is a new vision for space. The picture here on the right depicts the space defense architecture, which carries the modular transport layer, which the United States and allies are trying to ensure that we are able to connect these systems together and have a resilient future for the space architecture, whether that be at LEO, MEO, or GEO. Raytheon and Collins are really trying to take these requirements, this feedback from our user community, and shape our future offerings to industry. And we always welcome feedback to that effect. In the next chart, you'll see where our focus starts to lie. M-code is what we like to hold as the golden standard. Congress set policy in 2017, required the upgrade to M-code. The M-code system is available today based on limited use and early use. In the near future, it'll be fully available to all users that are authorized to use its system. Likewise, the commercial signals that are available with it. The key bullet there at the bottom is M-code is an amazing leap in technology. Capability it provides the warfighter, the civil community, allies is unmatched. But in itself, it doesn't necessarily solve the denial, the deception, and the GPS-denied threats in its entirety. So we go to the right side of the chart, and this is really where Raytheon is focusing. We want to be able to bring the next capabilities and the alternative signals and the signals of opportunity to bear. Those could include, in the upper left-hand corner, new capabilities with the military. In the middle upper side, commercial signals, GNSS, QZSS. Perhaps military signals in the form of PRS, which comes from the European Union. On the far right side, there are experiments in NTS-3, Vanguard programs. Commercial services, LEO and MEO transport layers, and known radios and Earth-oriented objects, things like ELORAN. At the bottom, systems of systems can operate together with localized coordinate systems with time transfer. 3 different vehicles or 2 different aircraft can provide their own navigation to each other and complete their mission. And finally, the tried and true dead reckoning if you have an IMU, an acceleration unit, and a very accurate clock. And on the lower right side, there are systems in play at the classification levels to allow future. So the real question is, how can we bring these together? Why do we need all these signals, and what are we going to do about it? I'll jump to the next chart, which is the why. In the future, there's congestion, there's deception, there's denial, and there's loss. And we've seen all of this. Congestion in urban canyon environment. There's signal challenges, environments. It could be a mountain next to us. GPS signal prefers 4 satellites. If we can't get all 4, or the signals themselves are jammed by congestion, a lot of that can be taken out with proper design, filtering, and amplification. Raytheon uses that at its first level of defense in its design parameters, but we really focus on the next 2, deception, spoofing, repeating. These take the next level of capability, which are advanced algorithms, signal diversity, and really a SERPA multi-channel antenna can do a lot to help with that. Denial. Jammers can overcome about any level of power if there's enough power in the jammer. If you have the highest end anti-jam system, you can cut through that. The nice enabler is we've actually had some breakthroughs in the high level of anti-jam that even with the most challenging jammers known today and the ones that we think will be available in the next 5 years, our anti-jam algorithm will actually give you enough resistance to that if the GPS signal is there, you will always be able to see it. That really reduces the overall requirement set and the cost of the overall systems if we really are looking at jammers. And then finally, loss of the constellation. The GPS constellation is unavailable. We really do have to focus on alternative signals and sensors. At Raytheon, we try to view each of these from a technical discriminator to focus with our customers on if they want to operate through all 4 of these conditions, 3 of these conditions, 2 of these conditions, or 1. Now, for my last chart, I'll talk a little bit about what we're doing in the technology. In order to overcome all 4 of these, a lot of questions get asked on what we are doing about fusion and capability. The P&T assurance starts with the technologies that we have to ensure the signal is available. What we do is we have high anti-jam, advanced anti-spoof filters, and what we mandate is that signal is assured and available and correct. For us, PNT resiliency is using the dynamic capabilities of other sensors. That could be other signals from space, other signals from ground, or an IMU. And what we're focusing on doing is taking those anti-spoof, anti-jam advanced algorithms, the sensor capabilities, and looking for things that might be wrong with the architecture. If we detect something that is wrong with the architecture, what we can do is set up with the customer a Markov decision tree. This is not free-form machine learning, but it is a unique capability to define a set of decisions that allow the specific customer to be okay with the properties we're moving forward. So if we detect something, we will move to the next best thing, whether that's an inertial system, a GNSS, a space signal that's up already, target sensors, or time transfer, the next capability of the future. And based on each customer's desire point, we will weight that capability against the known signal from GPS. If GPS is unavailable, we will take the weighting of that signal and enhance it. We then add each of those weightings of those signals to combine them to give the best PNT solution. The future is really to have a fusion capability, a transfer of time and knowledge, and keep the tried and true availability of anti-jam at the forefront of the great capability provided to us with M-Code. That's really where we see ourselves going in the world of anti-jam as the premier defense, the algorithms for the secondary, fusion for the tertiary, to make sure that we can have a truly assured and resilient PNT architecture. We welcome any questions that may come, but right now I'd like to hand it over and introduce Roger Hart, Director of Spirent Federal Systems, to talk a little bit more about multi-sensor simulations.
All right, well, thank you, Ben. Again, I'm Roger Hart, Director of Engineering with Spirent Federal Systems. So I'll continue in my presentation with this theme of multi-sensor integrations and fusion. Now, Spirent's best known for our GNSS simulators, long history of that. But today we'll talk about our work in integration of non-GNSS sources into simulations. We'll talk about where we are and then get into one corner of our developments, the implementation of an open Ethernet interface for supporting various sensor types. Topics we'll cover, I'll give a brief introduction about Spirent Federal Systems. We'll talk about the support that we do have currently for non-GNSS simulations. Talk about the evolving need for open standards for sensor simulations and our effort that we've got going to implement an open Ethernet interface into our tool suite. The Spirent Federal Systems was established in 2001 as a U.S. proxy for our parent company, Spirent Communications, that Ajay, who will follow me, is part of that. Spirent Federal was established to serve the U.S. government and contractor laboratories specifically. We have about 25 employees across the country providing sales, engineering, and post-sales support. So as our relationship with Spirent Communications, Spirent Federal is able to offer the full line of Spirent position navigation timing products, and then additionally developed in-house at Federal, we can provide Y-code and M-code solutions to authorized users. So Spirent simulation solutions are really considered the de facto standard in government and contractor laboratories across the country. And to achieve that requires constant innovation and development. So today's presentation will discuss just one corner of an emerging area of development. So global navigation satellite systems, GNSS, which encompasses GPS, GLONASS, Galileo, Beidou, and a number of the regional systems as well. Collectively, GNSS is a real newcomer actually in a long history of navigation system developments. So GNSS provides instantaneous, global, all-weather position fixes with unprecedented accuracy. So no longer do you need an understanding of spherical geometry and how to read ephemerides. So the basic training is pretty much learning where the power button is. So the tremendous benefits that GNSS has offered has led to a proliferation of applications and a high reliance on the technology in our daily activities. However, in recent years, there's come a growing concern that we've become overly dependent on GNSS alone. So with the signal structures widely understood, easy access to RF generating tools, the vulnerabilities of GNSS to interference, jamming, spoofing have become more apparent. But the combined use of the legacy non-GNSS sensors along with GNSS can aid in mitigating the vulnerabilities of GNSS. So for improved integrity, performance, autonomy, there's a very high interest currently in using multiple sensors in a variety of configurations for doing navigation solutions. This leads to a wide variety of sensors in different forms that are available. And so along with this evolution, there's a perception for a need for standardizing interfaces between the various sensors. So the chart I've got here, it's not an exhaustive list, but it illustrates quite a number of the navigation inputs that are currently being used and integrated into vehicles. GNSS there, of course, are our prime interest for a lot of years at the top there. The picture's an automobile, but there's some mixture of these sensors to be found in airplanes, drones, spacecraft, marine vehicles. So some of them lend themselves to simulation alongside of the GNSS signal. And Spirent has implemented several of these, as I'll discuss in the following charts. Others are already well developed and very complex models that it doesn't make sense for Spirent to duplicate those efforts. So in those cases, our focus is on simplifying the integration between the different navigation inputs, and Ajay's got charts discussing more of that in his presentation. So you'll find through the system, through these sensors, a mixture of processor allocation. Of course, the GNSS receivers are they're standalone. They have a great deal of processing going on in them, as you'll also find with the vision systems and LiDARs and so forth. Others are simply pulses or an analog sensor. And so we've shown just kind of a generic nav processor here. This is where the sensor fusion comes in. You'll have a processor or a distribution of processors taking in those inputs and generating a blended, improved navigation solution that gives high accuracy and is robust against some of the interference sources. So Spirent's work in GNSS simulation started over 35 years ago. Our first simulator was a 10-channel, one antenna, GPS L1 only system that required pre-generation of the scenario data. As new GNSS constellations have entered the scene, Spirent has expanded support both in signal types and channel capacity. So the latest systems support all the GNSS types and multi-antenna for surface systems, multi-constellation, real-time hardware-in-the-loop configurations, including Y code and M code. So as our customers' mission requirements have expanded, we've been asked to add non-GNSS navigation sensor sources. So these have typically been added in response to particular system requirements, and so it's resulted in the evolution of several different products. So they include the ability to generate gyroscope, accelerometer, INS measurements, barometric altitude, heading, wheel speeds, compass headings and magnetometer outputs. I think there are a few others as well that covers the basics of them. So there's some overlap between the products, but because of the unique interface requirements that have been imposed, there's not one product that covers them all. So this is a kind of a quick look at where we are and what we see the direction of this multi-sensor integration. So currently, particularly with defense systems, we've seen systems built up from a number of discrete boxes. So these can be sensors, also communication packages in that. So you'll end up with a system with a number of different boxes. It's not unique to the simulator situation I was talking about, but the actual implementation of vehicles, we'll see these discrete packages with separate hardware interfaces. They'll have commonly RS-232, RS-422, mil standard 15.3, Ethernet, pulses, voltages, and it continues. All of which that navigation processor has to have an interface for, electrical interface, has to accept the data and interpret all those different forms, which are frequently proprietary interfaces as well. So what's seen as a more elegant method of integration brings us to this concept of sensor fusion. There's a lot of work going on presently. Particularly, you'll hear about self-driving cars, work in that area, delivering packages by drone automatically, and that are type of applications that are making the news frequently. So you'll see, I stole one of Ajay's pictures here actually, so he'll have the blow up of it. But you'll have a common processor accepting multiple sensor inputs. They'll often use artificial intelligence to produce an optimal solution. Actually one that could be a better solution than could be attained from any of the independent sensors. So from the previous chart, some of the perceived drawbacks of integrating the discrete units leads to larger size, weight, and power with having to have separate packages, separate power supplies. And so some of the examples of the vehicle on the previous page, it can actually be hard to fit the driver in there by the time all the equipment is integrated into the system. So it's difficult to maintain and integrate. It leads to situations where a particular vendor gets locked into an inflexible architecture. So to get past these drawbacks, today's users are really voicing a desire for open standards for sensor integrations. So having a non-proprietary interface allows for more vendor competition, be easier with the openly published interfaces for new entries to join the process of the procurements, simplifies integration. Once everybody's following the open standards, you can interchange sensors, should allow new technologies to be implemented more quickly. And on a number of defense programs, they have decades-long life cycles with periodic upgrades of the entire architecture. Having the open interfaces should allow incremental upgrades and a quicker refresh on some of these long-term programs. So there's probably always going to be a bit of a contest of will between the end user and the vendors. They can perceive it as good to be able to get locked into a long-term program for stability and timing planning. But having a standardized interface can lower development costs and lead to avoiding having to support a scatter of interface across the various product lines. So systems are becoming more complex. The government's very interested in developing these open standards, and down to the point even that, say, RF systems could be sharing components. So from the earlier chart, I talked about Spirent having developed some rather specific non-GNSS interface types. We are actively working with the government and industry to implement an open Ethernet interface for simulating the non-GNSS sensors. So key considerations of this, by its own name, have Ethernet connectivity. We need to be careful to maintain the realistic sensor modeling that we've invested in, and also the ability to control the error inputs, giving you the ability to generate a pristine scenario or one with real-life error inputs. It's important to maintain the low latency between control inputs and response to keep precise timing so that the non-GNSS simulation is tightly synchronized with the RF generation of the GNSS. And of course, by the open interface, abide by a flexible format that's openly published. So as we're looking at our products, first steps are going to be to take the existing products and update that to adhere to the open interface, probably individually, and then ultimately have a merged solution for that. Okay, so just a quick picture of basic elements of the system. You've got multiple sensors physically connected via an Ethernet. So each sensor has logic to output according to the rate and formats established for that sensor type. The navigation processor will have a text-based configuration file that will know how to interpret the information coming back. And in navigation, timing is the key here. So you'll see there's two components to that. There'll be a frequency reference so that keeps everything operating at the same rate and keep them from drifting from each other. And then there'll be time synchronization message going out over the Ethernet so that each of the units has time. So as long as they follow the interfaces, the sensors should be interchangeable between different models and manufacturers. For the simulator, actually you just have one box on the left hanging on the Ethernet, which would be outputting multiple sensor types. And so the navigation processor over on the right wouldn't be able to tell whether it was receiving simulated data or the actual sensors there that are all adhering to the same. Okay, so what does this mean for Spirent products? Here's a little bit different look in the table here at the interfaces currently supported. So we do have some that support Ethernet already, as well as RS-422, standard 15.3, and some voltage levels in there. So we do have some support for Ethernet, but those are developed to specific interfaces, don't support the open standard. So it'll be natural to start with those, to convert those over to the open Ethernet interface, followed by the other sensors, and then this will put us in a good position to add additional sensor types down the road there. So we do have some near-term needs for these open Ethernet interface, and we expect our first release of this mid-2021. So just kind of wrap up, navigation systems are really evolving at a rapid pace. So making simulation, both GNSS and the non-GNSS that we discussed here, a really dynamic environment. So implementing an open Ethernet interface here is just one of the active development areas that are meant to keep Spirent apace with navigation developments. So following me, Ajay will continue with that theme. Just as a parting note, we'd like to alert our viewers that Spirent Federal's premier annual PNT GNSS training seminar is, as things are this year, going to be virtual for the first time. As usual, there's no charge to attend. For the convenience of the attendees, instead of a full day, we've broken the seminar into 4 different sessions that will each last around 2.5 hours on 4 different days in March, Tuesdays. So you won't have to block out a whole day from your schedules. We'll try to digest all the information at one setting. So if you're interested, more details on the full agenda and how to register can be found at our website, spirentfederal.com. So with that, we'll turn things over to Ajay. Thank you.
Thank you, Roger. Good morning, good afternoon, and thank you for staying with us. For this last leg of the presentation, we have put together information on our concept, our visualization of how a sensor fusion validation can happen in a multi-sensor environment, in a realistic multi-sensor environment. Let's really take a quick look at how we've organized the rest of the talk. About Spirent Communications, we'd like to start off by introducing Spirent a bit, and then we will transition very quickly into the complex landscape of testing possibilities, given the nature of the systems and the subsystems in today's advanced technology platforms. As a third topic, we will then discuss briefly regarding the need for realism in a simulation environment. And finally, we will review how all of these individual pieces can be put together to form a sensor fusion framework that will enable you to develop, test, and deploy the sensor fusion algorithms at a rapid pace. Quick look at Spirent. So Spirent is a test and measurement company and has an industry-leading portfolio of test systems and services to support the development of various technologies such as 5G, Wi-Fi, cloud, positioning, navigation, and time, which I will hereafter be referring to as PNT. I'm here today representing our PNT business. Between Spirent Federal and Spirent Communications, which is a parent company, we have about 200 employees focused on PNT technology evolution and development. Spirent's PNT solutions work behind the scenes to improve location and timing accuracy, reliability, and the robustness of your systems. As PNT systems are getting complex day by day, year after year, we're also constantly evolving our test solutions to meet the industry demands. Spirent's PNT journey started off with GNSS simulators back in 1985. We were one of the pioneers of GPS simulation equipment. Since then, Spirent's capabilities and services have grown to meet the needs of the industry. The depth of knowledge and experience we have is an important success factor, we think, with many of the current team members having been involved in the business from its very early days. Today, Spirent simulation systems are used across the world in over 25 countries and in every continent. Our innovation continues to date, and we've not stopped improving our product. We are the only company that offers both simulation as well as record and playback capability. We launched a record and playback product in 2015, and it has been a great supplement to our simulator product line. Spirent simulators provide multiple outputs for SERPA testing and fixed radiation pattern antenna applications as well. Our simulators can be used for inertial simulation, can include all the GNSS constellations, all frequencies. It can also include Y code and the latest M code in the simulation environment. With that said, I've covered a quick intro into Spirent. Let's dive into the details of why and how you should evaluate the sensor fusion algorithms. It is very important to note that the amount of complexity that is being packed into typical platforms is beyond imagination. Here, in this case, on the slide here, we have an image of an automotive, but it really applies to any other platform, be it a drone or a mobile phone. There are lots of subsystems that are working in synchronization to make the overall system work and give a nature of ease and user acceptance. With this level of complexity comes the need for rigorous validation to ensure that the subsystems are functional and are aligned, and these subsystems are communicating with each other in order for the platform to have the desired user experience. Today, Spirent across its various teams can help in all these domains, from connectivity to PNT testing into virtualization, cloud, Wi-Fi, and 5G. The picture here is just presented as an example. If you look at all the applications that use location, it is fair to say that location need is almost everywhere. Some applications are safety critical, while others use location data for convenience and tracking purposes. The level of testing and the amount of sensors packed vary widely across these applications. For safety of life applications, there is real need to test for corner cases that are not possible to be reproduced in real life. Such scenarios are best simulated and tested in a realistic simulation environment. In order to have realism to your testing in the lab, we have started to pull in 3D models that help you put together a rich local synthetic environment inside the lab. Having a synthetic environment by itself is not going to do any good unless we assign the electromagnetic properties to the materials. And these properties are permittivity, conductivity, the thickness, so on and so forth, to the various materials that are in the synthetic environment. Once we have these parameters assigned, we can then use ray tracing mechanisms for signal propagation and compute how these signals interact with the environment. In this picture here, we can see three kinds of rays. One is white, which is direct line of sight, blue, which is diffraction, and red, which are reflected. Now, by doing all of this, we are now not only modeling the GNSS errors due to satellites, clocks, and troposphere, ionosphere, but also giving the users a chance to model the environment around the receiver. Depending on the test need, we import 3D mockups of complex scenes. These scenes could be scenes with buildings. These could be scenes with a military environment, or these could be scenes of a highway with a fast-moving vehicle. In order to complete the implementation of a synthetic environment, we also need to add physics to the moving objects. Now, this is really important so they obey the laws of physics and laws of real world. Now, as you can imagine, there is a lot of computation that is happening behind the scenes to bring you this richness in testing. We work with a French company named Octal-SC to make all of this happen. In addition to everything that we have discussed in terms of 3D scenes, it is also a good idea to add more accurate vehicle dynamic models to the simulation. Again, with the objective to turn the simulation more realistic. There are players out in various markets. I can give you an example in the automotive market, such as IPG or AV simulations, who have a lot of expertise in vehicle dynamics. Now, similarly, there are other players in other markets who can give us reliable input of the vehicle data. We have made it very easy for various vehicle simulators to send trajectory or vehicle data into our test environment. With the synthetic environment, with the realistic vehicle dynamics and the trajectory, we can make this test environment much more realistic. Most applications are using GNSS and inertial units together, right? So in some instances, we have seen other vehicle sensors also being used. Vehicle sensors can include heading information, wheel rotations, ticks, vehicle direction, backwards, forwards. All of this additional data will help improve the PNT integrity and availability. Typically, all of these sensors are treated as aiding information into GNSS. Teams designing nav filters using multiple inputs from these sensors have to be mindful of the kind of sensors to be modeled. For example, if a high-end IMU is being considered for design, not just the bias drift and random noises be considered for filter states, but all the other errors should be added on to help improve the fusion mechanism. Simulation will allow design teams to inject the right IMU faults. Not just IMU faults, but any sensor that is being modeled in the framework that you see on the picture, GNSS, accelerometer gyro, mag barrel, or vehicle-based sensors. All of these sensors being in the simulation environment give the user a flexibility to simulate corner cases, to simulate outages, to simulate major errors, to understand how will a system work in absence of one of these sensor inputs. If you're an integrator, you can use a simulator to evaluate if a tactical grade IMU is worth the extra cost, or is a consumer grade with a better GNSS antenna and receiver a better suited option. These trade-offs need to be well thought through, and this is one area where simulation really comes into the rescue. This slide, we wanted to give you an idea of how a system with all of these different parameters that we spoke about, with 3D mock-up scenes, with different sensor modeling, with realistic vehicle input, including the dynamics. We can put all of this together. This is an example of how a system with all of these integrated can look like. A 3D scene on the very left-hand side of the monitors, a trajectory and vehicle dynamic model via a third party. This trajectory can be modified on the fly using a joystick and a steering provided, multiple sensor simulation, and a receiver that shows the output. We want to give user every tool that is really needed in order to validate the sensor fusion inside the lab before it gets deployed. That is our goal, and we will constantly look forward to evolve and enhance the products that we have today. That concludes the talk. I will hand it back over to Mackenzie. Thank you so much.
Thank you all. That was great. At this time, we're going to jump into some questions we received during registration and a couple we got during the presentation. My first question is for Ben. Apart from policy issues, from a technical standpoint, for example, time to first precision, do you see a benefit at fusing directly GPS and other PNT sources such as other GNSS signals?
Great question. Yes, is the short answer. The longer answer is alternative navigation, signals of opportunity, fusion sensors can help augment or replace GPS. So there is a lot of capability in them. We have looked at using those alternative signals, whether they be space-based, airborne-based, or ground-based, to check the assurance and the precision of GPS. We have been able to successfully in the lab use them to increase the performance. Specific to the question of time to first fix and precision, I think there is an advantage, but it's specific to the application. And what I mean by that is, depending on the challenge of the environment we are in, the algorithms we have right now will bring GPS up the fastest. But if there are any challenges, as we said in the threat domain of congestion, denial, deception, every single time there is a benefit to having those alternative signals to verify those. So absolutely, GNSS, QZSS, LEO constellations, MEO constellations, airborne, and a very accurate time clock all benefit the overall performance of these systems. And we really are seeing that in the next generation of receiver chips.
Great.
Thank you.
All right. Yeah, this next one is for Roger. Roger, can you please comment on the requirements for IMU technology when developing sensor fusion testing?
Sure. It's really an engineering question, so it often comes down to size, weight, power, and performance. With IMU sensors, there's a wide range that cover all of those. So certainly for a cell phone antenna, you've got to have something that's going to fit in there and be able to run off a battery. An aircraft navigation unit using a fiber optic gyro or ring laser gyro or something simply not going to be something you're going to put in your pocket. So they're going to, some of those requirements are going to be driven by size. Performance is a leading concern as well. So some of the key parameters for IMU systems, particularly drift, depending on how long you need to navigate off that IMU solution, can be a key factor. So often the MEMS gyros and that are good for small applications, and then you get into the laser-based gyros for the higher performance. You'll want to look at noise and sensitivity, your ability to sense accelerations, rotations. So those would be the key parameters that you're going to typically run into as you are evaluating an IMU system for integration into your navigation testing.
Great. This next question is for Chad. Will existing Raytheon Ajay antenna systems work with the Collins PNT systems?
Thank you, Mackenzie. The answer is yes. The key is designing to the right standards, which sometimes are legacy standards and sometimes they are brought out by our customers. But even before the merger, we frequently worked with Collins and collaborated on navigation solutions. The government and customer people here will have heard the term competimates. And with challenging requirements and things getting harder and harder, that's frequently the case that we in industry have to collaborate across company boundaries to provide the right solutions. And we try, all of us in industry, try to design to some of those open standards or DoD standards to make the products interoperable. In our new company, as Ben mentioned, we have a lot of overlap and complementary technologies we bring to bear at different levels, but that legacy is and that's give us more opportunity in the future. But yes, we do. Our anti-jam systems have been designed to those standards, so they will work with various receiver level products and in various platforms. Thank you.
Great. All right, this question is for Ajay. When will M-code be fielded to U.S. and allied forces, and why has it taken so long to do it?
It would be ideal if Roger can help me out. Roger, can you please take this question for me, please?
Sure. So we are, within the next couple of years, looking like to have the full capability. So all but, I think, 8 satellites in the GPS constellation are now M-code capable. The ground support is reaching the ability to support full constellation operation. So I don't want to hazard speaking for the government and when that will all be ready, but existing programs, new programs are under directives to procure and implement M-code receivers into their systems. So in the next couple of years, I believe we'll see the full capability being released there. So as to why it's taken so long, I can't hazard I guess on that one either. It's been a complex system with shifting requirements, and part of it has just simply been that the old set satellites have lasted so long that they've been able to slide those to the right. So there's a real effort now. We're seeing the GPS-3 satellites being launched, and I think we'll have the full capability before too long.
Okay. Ajay, I have another question for you. Sorry about that. How do you propose to compare the quality of Fusion application solutions?
Right. Yes. So the real comparison really differs from application to application. Some applications do have heavily weighted GNSS solution, whereas others have heavily weighted IMUs and WheelTech information. Depending on the application, the weightages differ, and a simulation can really help in simulating ground truth while also giving the user the flexibility to create outage scenarios, either in case of GNSS or errors in case of IMU. So different applications, different scenarios. We are here to help. If there are more specific requests, we are more than happy to help you out.
All right, I have another question for Ben. Is new Raytheon Technologies business interested in civilian PNT market? And are any of Raytheon's Ajay and sensor fusion technologies applicable to commercial applications, or are they mostly military?
That's a great question. We have 4 different levels of anti-jam products. And so yes, the answer is we are interested in commercial. We've been looking at an avionics market application, especially with some of the challenges in the news recently occurring with jamming on commercial airliners. Some of the shipping challenges from vessels in the sea as they near countries and contested waters. Our current systems do work with commercial code. They are available, depending on the capability, for sale to commercial partners, foreign governments, and obviously our U.S. allies. We do have some specific military anti-jam, but all of the legacy is wrapped around together. I do believe we are very interested in both commercial and military. So yes, I appreciate the question.
Okay, great. This next one is for Chad. Galileo PRS will become the standard in Europe, and defense agencies are expecting to take benefit of both M-code and PRS to improve navigation resiliency. What is your opinion on this trend?
Thank you, Mackenzie. It's another great question. The open architecture and modular solutions are being designed to be adaptable to all the changing environments. We, in our company, have actually been working on a dual mode receiver with Galileo and GPS for military users for over 3 years now. And we are designing that system to initially incorporate open service use of Galileo and combine it very tightly integrated with the military GPS signals for avionics applications and resilience. And when and that will be available for U.S. customers initially in that format, It can also be made available to foreign customers who are allowed access to M-code and who want to put in the PRS signals. And when policy allows, we will be we're designing that system around those open interfaces such that we can insert the PRS chipset from our partners that develop that with our GPS chipsets into the same box and use the same external interfaces for the platform. So that's what we talk about, being able to evolve what's inside and minimize new integrations at the platform level. Thank you.
Great. All right. For our last question, this is for Ajay. On the real working setup display, how is the ground truth generated and displayed, and how is the sensor fusion output compared to it?
Right. Yes, I think that is a very good observation from the slide. The way it works is we get a trajectory source input from a third party. We log that, and we use that as the ground truth because that is error-free. And that would then become the ground truth. We will add errors on top of that, and the output will include the errors. Now, once you start looking at the output measurement and compare to the ground truth, then you do definitely see the errors. One way of looking at it is by having a sensor fusion at the other end and comparing it against the log data, which then becomes our ground truth. So again, this is the advantage of having a simulation environment. Once you have a simulation, we know what we are simulating, so we know what the ground truth is. And because we know what errors we are adding, we also know what the errors are. This gives you a really good understanding, helps you do the analysis right.
Great. All right. Thank you all for attending today's webinar, GPS Anti-Jam and the latest in sensor fusion testing, brought to you by GPS World Magazine and our sponsor of the event, Spirent Federal Systems. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you see on the slide. The resources panel houses a PDF of today's presentation slides, which you can download. To access this panel, click the green icon on the far right end of the toolbar at the bottom of your screen. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World also will be posted to this page. Thank you all for attending, and we'll hope you'll join us for another great webinar.